we can talk about the heat of fusion, right? The heat of fusion. Well, what is actually the heat of fusion then? The heat of fusion is actually the energy required, or that must be added to convert exactly 1 gram of a solid to a liquid at its melting point, right? So we'll use water as our example here. The excuse me. We'll use water as our example here, and for water, 80 calories or 334 joules of heat is required, right, to melt 1 gram of ice at 0 degrees Celsius. That's its melting point, right? So that's why we have here in our heat of fusion equation, if you have solid ice plus 80 calories or 334 joules per gram, the solid water or ice becomes water. And this is actually a reversible reaction, right? Because you can do it the other way, where if you had liquid water and you froze it into solid water, you get out of it the same amount, 80, 80 calories per gram of water and 334 or 334 joules per gram, right? So let's try to figure this out. What if we had 32 grams of ice, right? What if we had 32 grams of ice? How much energy is required to melt that guy, right? Well, that's super simple. So again, uh, we'll use the some dimensional analysis and some unit conversions. We'll start out with our 32 grams of water, H2O solid, right? That's what that is, H2O solid. And that's times the amount of energy that we're putting into it to melt it. So again, we always use, chemistry likes to use joules, so we'll use joules. That's 334. And we should look more like a 3. There we go, 334 joules for 1 gram, right? The 1 gram comes from this gram right here. That times the conversion, right? Because we always want our answer to be in kilojoules. For every 1 kilojoule, there's 1,000 joules. Because remember, for some reason the SI unit is like joules, right? Or kilojoules. Um, so we'll go ahead and do that calculation there. I'll switch back over to the calculator view. And I'll start out by clearing our last calculation. And we have 32 times 334 times 1, right? And I could have put parentheses there, but I'll just go ahead and go enter, and then we'll divide that number by 1,000. And that gives us 10.688, right? So we needed to be 3 sig figs, right? Because our smallest number of significant figures is there, 3 significant figures right there, right? Which means that is going to be then rounded up to 10.7 kilojoules. That's how much energy is required to melt 32 grams of ice. Fun stuff. So, excuse me. Water can also not just melt and freeze, but it can also evaporate, right? So evaporation occurs when water molecules gain sufficient amount of energy to escape the liquid surface and enter into the gas phase, which you could probably see that definition better if I got the calculator out the way. There we go, right? Um, at its boiling point, the molecules have enough energy to overcome their attractive forces, and that's why they become a gas. So essentially, whenever anything evaporates, the molecules are getting enough energy so that they can repel each other, right? And They're basically, like it says in the definition, it's overcoming their attractive forces, and they become a gas, and that's when a liquid becomes a gas. And then so the definition for heat of vaporization is being blocked by my head. So let me go ahead and minimize my head real quick. The heat of evaporation, much like the heat of fusion, it says the heat of evaporation is the amount of heat absorbed to change 1 gram of liquid water, 1 gram of liquid to gas at the boiling point. And I'm just using water as an example because we have water right here. So in this case, the amount of water, the amount of energy needed per 1 gram is 2,260 joules per gram, or 540 calories per gram of water to evaporate it, right? To get it to its evaporation point. So that's very similar to what we did with the heat of vaporization, but instead of it melting, the water is actually evaporating. Or sorry, the heat of fusion, but instead of doing melting the ice or freezing the ice, we're actually evaporating the ice, or evaporating the water. But since we're also evaporating water, the opposite of evaporating water is actually condensing the water, right? They're reversible processes. So the same thing can happen again, where if you have water as a gas, water vapor, and you cool it down, right? You actually so it condenses, right? The water becomes liquid, and you actually release 540 calories per gram, or 2,260 joules per gram, right? So the definition of condensation is when water vapor is converted to liquid as water molecules lose their energy and slow down, right? So the heat of condensation then is the amount of energy released when 1 gram of gas changes to 1 gram of liquid at the boiling point. So the thing to remember here is that both vaporization, right here, and condensation occur at the boiling point of the liquid, right? So let's do an example that demonstrates this concept. How many kilojoules are needed or released when you have 50 grams of steam that form from a volcano that condenses at 100 degrees Celsius? Well, of course it's 100 degrees Celsius because we're talking about steam, right? Steam is just water, and condensation and vaporization happen at 100 degrees Celsius, so that's kind of a given. They didn't even have to give you that. You should have known what it's going to be if they're talking about steam, right? So the only thing you really need here is the number of grams of steam, right? So let's do some dimensional analysis and figure this out. So if you have 50 grams, and you don't see my face, so I'm going to put my face back up. There we go. So if you have 50 grams of water, which is vapor, so it's H2O gas, right? You can multiply that, again, the same way we did in the last heat of fusion one, except this time it's a different number because it's heat of condensation slash evaporization, right? This number is going to be 2,260 joules per gram, right? We always want to convert this into kilojoules because it's going to be a big number if we don't. For every 1 kilojoule, there is 1,000 joules, right? So we calculate that in the calculator. You're not going to be able to see it, but I'm going to let's just calculate and I'll put it back onto the writing. 50 times 2260 times 1, right? And then divided by 1,000. So we get 113 kilojoules. Let me show that real quick. There we go. 113 kilojoules. Pretty cool, right? And then, if we want to do our significant figures, this number actually here was given as 50.0, which I should have put a 0 there, right? So that means that this number here had 3 significant figures. this number here had three significant figures. Or sorry, four significant, no, sorry, three significant figures, because the 0 is not significant. It's a placeholder. And then this doesn't matter because it's conversion, right? So three significant figures, three significant figures. Look at that. We don't even have to change anything about that. So that's how much energy is required to, how much energy is released when steam from a volcano condenses. 50 grams of it, right? How about we do something a little bit more practical? Something that happens to me a lot because I like to burn myself, right? I'm going to clear this out. Okay. So I burn myself with hot water a lot. And say I had 25 grams of hot water. What do you think is actually burning me more? The hot water itself or the steam from the hot water, right? Well, let's calculate that out. Hot water? Yes, 25 grams of it actually, right? Nope, not 25 Celsius, but 25 grams of hot water. Let's figure that out. Well, let's first figure out how much hot water is going to burn me. So we have 25 grams of hot water. Okay. We multiply that by the change in temperature, right? So you're going from 100 degrees, which is hot water, right? And it's got to cool down to release heat. That's how you get burned, right? And so we're cooling down to my body temperature, which is 37 degrees. Remember that from the previous slides, right? 37 degrees Celsius, okay? And then, since it's liquid water, we want to use the specific heat for liquid water here, right? Which we talked about before. 4.184 joules. Gram per Celsius. 1 gram Celsius. Alright? And so using that, we can figure out how much heat is released just from the water. Or energy is released just from water. So let's go ahead and show you the calculator calculation. So we have 25 grams times, again, another time when you need to make sure you have your order of operations correct because you want to do the delta T first, or change in temperature first, before you do anything else. So that's 100 in parentheses minus 37 degrees. Right, that's a change in temperature. That's boiling water losing heat, right? Cooling down, losing heat. That's how you release heat to my body temperature times the specific heat of water. 4.184. I messed up, I think. There it goes. 1.184. There we go. So the answer you get is did I do that right? 25 grams minus 137 4.1. Oh, I did that backwards, that's why. It should be 8.4 there, not 4.8. There we go. There we go. I thought that number looked a little low. So the amount of energy released, or heat released, when the water cools down and releases its heat and into my body, burning me, right, is 6,589.5. Oops, sorry, 0.8 joules. 0.8 joules, right? Well, let's look at our significant figures. Lowest one here is here. 2 significant figures for the grams. Oh, let's do some canceling out, by the way. Yeah. Grams cancel out here. Grams cancel out there. Make sure that we end up with just joules. Celsius is there. Cancel out Celsius. And now we're left with the joules, right? That's how you check yourself to make sure you got your units right. And we have two significant figures, so we need to make this two significant figures. That 8 there rounds that 6,500 up to 6,600. And now we have 6,600 joules. So that's how much energy is being released, or heat's being released, when hot water touches my skin and cools down to my body temperature, right? Let's see how much it is when it's, how much heat's released or energy is released when it's the steam condensing on my skin. Just condensing, right? So again, we'll start with 25 grams of water. And this time, instead of using the specific heat of water, we'll use the heat of condensation of water, which is 2260 joules per gram. And we'll calculate that real quick. That's 25 times 2600. 2260. And the answer there is 56,500. Again, we're going to need two significant figures because we have two significant figures right there as the lowest. So that rounds that up to 5,700. Oh, sorry, 57,000 joules. So water, just hot water touching my skin only releases 6,600 joules. But steam condensing on my skin releases 57,000 joules. Wow, that's a big difference, right? We can add both of those numbers together, and we'll get the total amount of heat that's released in your skin when you burn yourself with hot water, with hot boiling water, right? And you add it all together, 6,600 plus 57,000, and that makes it 64,000 joules. So when you burn yourself, that's how much water, that's how much heat from the water is going into your body, and that's why it hurts so much when you burn yourself with boiling water.